The first major type of spatial data is vector data. So vector data represents the world using points, line, and polygons. So a point can represent a tree or a sensor or restaurant. And as you can see, it has latitude and longitude or X and Y, and the type is set to point. A line can represent a road, a river, or utility pipe, and we have to set type as line string, as you can see in this slide. A polygon can represent a building footprint, or a parcel, or a city boundary, or flood zone. So vector data is great when the object has a clear shape or boundary. So this is why vector data is common in GIS, in planning, transportation, utilities, infrastructure. And when we say similar to what we have as JSON format, if we include location information in JSON format, we call it GeoJSON. As you can see in here, we have three different types of GeoJSONs. We can have vector data as shapefile, and we usually work with shapefile in AEC industry or architectural engineering and construction. However, we have this option to convert shapefile to GeoJSON, and there are some important notes that we need to include whenever we do the conversion. We're going to talk about this later in another episode. So these three examples that you just saw are the main types of vector data. That, however, there are different types such as multi-point, multi-line, multi-line strings, and multi-polygon. The second type is raster data. So raster data represents a space as a grid of pixels. Each pixel has a value. So that value might be color, elevation, temperature, vegetation index, pollution level, or probability. This is the format behind satellite imagery, aerial imagery, elevation models, heat maps, and many environmental data sets. A simple way uh, remember um, to remember it is vector data represents objects while raster data represents continuous surface. So raster data is somehow similar to images. So a road is usually a vector line, and elevation across a landscape is usually a raster grid. Similar to the pixel values concept that we have in images, in raster data, we have similar concepts. We have pixel value for raster data. Point clouds are another important special data type, uh, especially in engineering and construction and surveying and digital twins, where you want to compare, for example, existing condition with proposed condition. You can use point clouds. A point cloud is made of millions, sometimes billions of 3D points, and each point has X, Y, and Z coordinates, and some points may also have color, intensity, classification, or time step. And point clouds are usually captured by LiDAR scanners and drones or mobile mapping systems or photogrammetry. And they are powerful because they capture the real world in high detail. So instead of drawing a building manually, we can scan it and get a dense 3D representation of its surface, or sometimes we call it as is condition or existing conditions. So now let's move from point clouds to structured 3D models. In point clouds, um, we get so many points in a space where we have to do classification, we have to do segmentation, we have to label the data, and in 3D, however, um, it gives us a structured geometry, so we already have those information. So it can represent walls, it can represent floors, windows, pipes, beams, roads, bridges, basically assets in buildings. So in AEC world or in architectural engineering and construction world, this often means um, when you include information to the geometry, it is called BIM or building information modeling. That's one difference between 3D and BIM. And it can have multiple formats. The 3D model can have multiple formats such as IFC, Revit, DWG, and so on. So this type of spatial data is very important for digital twins because these models or these elements of the 3D models are geolocated. So when they are geolocated, then we can consider them as spatial data. And we don't need to just know where the, the element is located. We also need to know more information about those elements. We need to know what is their material, what is the actual start date, actual end date, and different kind of information that can impact decision-making process later on. The next type of spatial data is network data. So network data represents connected systems. Instead of only storing geometries, network data stores nodes and edges. So nodes are connected points and edges are the links between them. A road network has intersections as nodes and road segments as edges. So a transit network has stops and routes. A utility network has junctions and pipes or cables. And this structure lets us ask questions such as what is the shortest path, or which areas are reachable in 10 minutes, or what happens if one road or one pipe fails. So network data is essential for routing, planning, logistics, mobility, utilities, and resilience analysis. The next type is spatiotemporal data. That means we have location and time. So this is what we use when something moves or changes over time. For example, a delivery vehicle moving through a city, or a weather sensor reporting temperature over time, or a land use map changing every year. So here we see three examples using GPX format. A waypoint is a single location. It has one element called WPT. This shows a single point. Then we have a route, which is a planned path. So inside route we have RTE. That RTE shows the planned route or ordered waypoints. And then we have track. Track is the actual recorded movement. That the time usually is inside a track object. So often with timestamps and elevation, we can find these two as well. This distinction matters because planned movement and um, observed movements are not always the same. So in geospatial AI, spatiotemporal data is extremely important because many real-world systems are dynamic and they're not static.